Okay, so good afternoon, everyone. Let's start. Okay, so before I dive into the lecture, are there any questions about either logism or any other aspects of the course logistics? Okay, and do try to keep track of the postings on Piazza. I have been kind of putting up notes out there based on questions from previous years, which you might find useful. Your question? No. Okay. Today's plan, I'm going to sort of wrap up the few remaining slides from the module we had started. One of the TAs, Wei, in his discussion section already went over them, but so it will be a repeat for some of you. But in one of the sections we didn't, so not all of you would have seen this. So when we had ended the last lecture, we had kind of talked about this the truth table, and that how you exhaustively kind of list in the truth table for every possible combination of input what happens, and then if some combinations of the input do not occur, then they become the don't care, and that was kind of the last thing we were covering. And don't cares basically mean that depending upon the whim of the designer, you can treat it as either a 0 or a 1, and usually whatever results in a cheaper design or a faster design or a design which may be more energy efficient. So that's what we were talking about at the end. And then the thing that we had just started on was kind of this notion that the truth table represents kind of a mathematical function. It does not have any memory, but rather it's a system where output always follows the input. So if you change the input, then the output instantaneously or with some sort of tiny delay reflects the corresponding entry in the truth table. So this is what shows out here, that on the input side, on the left side, we have n inputs, and on the output, there are m outputs. And basically, as I change the inputs, one of the bits goes from 0 to 1 or vice versa, or more than one bit, then the output will reflect whatever the truth table was implementing. There's a notational issue that you will notice, that on the left-hand side, the figure shows n distinct input lines, 1-bit lines. We often draw them in a compact fashion by, on the right-hand side, as you would see, that as a single line with a cross and an n next to it, and that basically means it's a bundle of wires with n bits in them. And likewise, on the output, we have m output bits, and we draw them as a single line with a indicating m. In logism, they have a notion of a bus, which serves the same purpose. So a bus can have multiple bits, and then they have a couple of components called splitter and combiner, I think, which basically can let you extract some of the bits. So like, for example, from an n-bit bus, I can say, give me bit number 5, for example. So the splitter kind of lets you unbundle the wires. Likewise, combiner kind of does the opposite. So in things like logism, it kind of saves you from drawing kind of a large number of lines, because oftentimes n and m can be quite large. But back to the main story, combinational logic are memoryless. So input changes, output immediately changes. Now, that's great, but oftentimes we need a notion of a memory. So let's say we are interested in making a digital calendar. So at the midnight hour, it's going to change to the next date. So in our case, the calendar has month, it has day of the month, so like 15th January, and then the day of the week, Sunday through Saturday. And the compute tomorrow is a function which takes today's representation and then converts it into tomorrow's. So in general, it would be complicated because you can have rollover happening across weeks or months. And this is a purely memoryless thing. It's a function which takes some input and creates an output, corresponding output, just a truth table entry. To make our calendar, we need to do something about updating things at the midnight thing. So what we assume for now is that there is this magical block which is in cyan color, and what you would notice is that at the bottom it has this input called midnight, and the idea is that at the midnight hour a pulse comes on this line, and whenever the pulse comes on this line, the output changes. So one way of thinking about this is that this is kind of like a mailbox or some storage entity, and the output always reflects whatever is in the storage. But the storage is updated only when the midnight tick comes. So at the midnight tick, whatever is on the input side, on the left-hand side, gets stored out here. So the stored part is updated at the midnight tick, and the output is basically just reflecting whatever is in the storage. So it's a memory element. You write to it when the event happens, and the output is always reflecting whatever is the current state of the memory. So in this case, right after the midnight, the stored entry out here would be today's date, and output out here is going to reflect that. And then at the next midnight tick, whatever is on the input out here will get stored out here. And what you see out here, what we are doing in the circuit is we take today's date, we feed it into our combinational block, which computes tomorrow's date, and then that is sitting on the wires out here. So we have a whole 24 hours to kind of do this computation. As long as this tomorrow's date is produced by the next midnight, we are okay. And at the next midnight, again, that process will repeat, and this kind of thing will go on and on. So this circuit has two types of things now. There is the combinational logic, which is memoryless, and there is this memory kind of element, which is called as sequential logic. So it reacts at certain times and responds to these events, which are often also called as clocks. So as you can see, there are kind of these two kind of entities, something which can store and something which is just a mathematical function. And this thing has these two characteristics, and it is memory, and it runs whenever an event happens. So you'll see a lot more of it in the latter part of the course. In circuit terminology, these things are called as registers. Registers, and that event input is called as a clock. So basically what a register does is, normally the output of the register just reflects whatever is stored in the register, and whatever is stored in the register remains unchanged except whenever a clock tick comes. When the clock tick comes, the current value of the input is put into the register, and then we wait for the next clock tick. Now, you might ask, what is this clock tick? Typically, clock tick is viewed as a rising edge or a falling edge. So, for example, we can define that whenever the clock goes from 0 to 1, then the update will happen. Or alternatively, we can define another way. Whenever clock goes from 1 to 0, then the update would happen. So that's a very typical way of dealing with this. Again, how to make that happen, we'll see kind of much later in the course. So we had kind of done this last time around. Now, one characteristic of digital system design, which kind of makes engineering very easy, is this notion that I can take simpler functions and then wire them together to create more complicated things. That's precisely what Logisim does. And in the discussion section, you would have already seen something like that. In this case, what we are doing is we are making something a little bit more complicated. What we want to do is we want to use our thermostat and the calendar, and then use that to turn the fan on or off. So what's happening in this case is that if the thermostat says temperature is too high, and today is so what's happening out here is you see this block called equal. So what this is doing is its output would be high whenever the two inputs are equal. So what it is doing is, if today's day of week is a Sunday, then this guy is going to be high. Then we see this block, which is a NOT gate. It's a NOT function. So it basically takes a 1, makes it into a 0, or takes a 0, makes it into a 1. So it inverts the logic sense. We feed it, and then we have this AND gate. So what's happening out here is we are basically saying that if it is not a Sunday, and temperature is too high, then turn the fan on. So if it is Sunday, this would be 1. So for this side to be 1, the input to NOT gate should be a 0, which basically means that there should be a mismatch out here. So what's happening out here is that we are picking these gates, AND gate, NOT gate, and this equal function, and we are kind of creating something more complicated out of it. So a NOT gate is an example of a primitive which is very commonly used, and it complements its input. 0 becomes 1, 1 becomes 0. AND gate, it outputs a 1 when both the inputs are 1, otherwise it outputs a 0. And these are just examples of a whole family of primitive functions which are commonly used. And if you look on the left-hand side of the Logisim navigation panel, you would see a whole bunch of them. So this shows an example, some of the things you will find there. So NOT gate we already saw, AND gate we already saw. There is this OR gate which outputs a 0 if and only if all the inputs are 0. So it's essentially saying that output is true if one of the input is true, true being 1. XOR gate outputs a 1 if and only if an odd number of inputs are 1. Another way of saying is that for a 2-input XOR gate, it will output a 1 if the 2 inputs are different. So if one is 1, the other is 0, or vice versa. If it were to be, let's say, a 5-input XOR gate, then we will simply count the number of ones, and if they are odd, then the output is 1. NAND gate, what you see out here is it's like the AND gate with a little bubble out here, and that bubble indicates a NOT function. So basically, a NAND gate is nothing but an AND gate followed by a NOT gate. So its logic is exactly the opposite, and a NOR gate does kind of the same thing to the OR gate. So these are examples of extremely primitive things. What we'll shortly see in the next module is not all of these are essential. In fact, everything digital can be designed if I were to only give you a NAND gate, a 2-input NAND gate, and everything else, all other functions can be constructed just simply from a whole bunch of a large number of 2-input NAND gates. In fact, a very favorite problem in a lot of exams is to kind of have students design something supremely complicated with just 2-input NAND gates. So you can design an arbitrarily complicated computer out of it. You can do the same thing with NOR gates. But you cannot do that with AND gates only. And the reason is, with AND gates, you can never do inversion, this NOT function. You can never invert the logic. And likewise, just OR gate is also not enough. Now, I'm going to ask a question. So let's say I were to give you the NAND gate, a 2-input NAND gate. How would you do, can you implement a NOT gate using that? So what I mean by that is, take a bunch of NAND gates, 1 or more, however many you want, and I want you to design a logic function which will do what an inverter does, which is takes 1, ties it to 0, or takes a 0, ties it to a 1. So would anyone like to take a shot? So you have NAND gates, however many you need, and I want you to implement a NOT gate.
Just connect the 2 inputs together.
Excellent. So you connect the 2 inputs together. So let's see what will happen. So if I tie the 2 inputs together, and let's call this guy x. Now what will happen is, if x is 1, then both the inputs to the NAND gate are 1, and according to what we have out here, the output would be 0. So if x is 1, then we will have 1 and 1, and the output would be 0. And likewise, if x is 0, then both the inputs would be 0, and the output would be 1 according to this logic out here. And that's exactly what a NOT gate does. What about NOR gate? Can you make a NOT gate out of that?
I have a question.
Yeah.
How did you connect the two? Were you saying that we have two same input, 1, 1, 0, 0?
I take my input and I feed it to both the inputs of the network,
Okay.
right? So electrically, that means I just short the wire. So how would you create a NOT gate from a NOR gate? Exactly. You can do the same thing. Okay, so now I have a NAND gate and I know how to make a NOT gate out of it. And therefore I know how to make a AND gate out of it, right? I can take one NAND gate and follow it by this NOT which was implemented using a NAND. And now I have an AND gate. So I can implement that. We'll see later, you can also do OR gate out of it, you can do NOR gate out of it, you can do XOR gate out of it. All of them can be done just from a 2-input NAND or just from a 2-input NOR. So these things are called universal gates. That is, just one type of gate is enough to create everything that is computable. Every mathematical function, every digital circuit which is possible. May not be most efficient, but you could do it. So we'll see more of it when in the next module on kind of the math behind it, if you may. Combinational logics have a property which is called as closure property. It's a mathematical term, but it basically says that if I take combinational logic and I wire them up together, that is, I take outputs of some and feed them into inputs of other, and as long as I do not have loops in my wiring, that is, it's never the case that I can kind of follow the wires and come back to the original point by jumping to the gates, then what I'll have is also going to be a combinational logic. That is, it will not have any memory. So, for example, what you see out here, see how I have taken the outputs of CL1 and fed them into CL2, and the overall thing, that assembly, if you want to call it CL12, then this closure property says that CL12 is also combinational as long as the wiring does not have any loops. And if you see out here, there is no loop in the wiring. I can never kind of start from a wire and kind of traverse this circuit and come back to the same place. So no loops means any assembly of combinational logic remains combinational. Now, if we do have loops, then it can have memory. Not necessarily, but it can. So let's look at this one. What do you think? Is this combinational? No loops, right? I mean, it's just straight through wiring. So this collection of these two combinational logic is still combinational. If I look at this one, it has loops in it, right? I can start from, for example, let's say this lower input of the top logic. I can go to the output, I can come back to the top input of the bottom logic, and then go to the output and arrive back out here. So there is kind of a loop sitting out there. And as a result, this is, in general, not combinational. And I say in general because in some special cases, it may turn out to be combinational, but in general, it is going to exhibit some memory. And in fact, later in the course, we'll see registers are made using kind of structures very much kind of like these. So, so those weird memory-full circuits can be designed from using the very same combinational logic thing, our NAND gates and all, but we are going to wire them up so that there are loops in our circuit. Okay, so sequential circuits, or
just have a question. So if a circuit is closed, I mean it's not closed, then it's a combinational circuit. What exactly is a combinational circuit?
Combinational circuit is one which doesn't have a memory. So it basically means that current output will only depend upon the current input. It doesn't depend upon anything in the past. Okay, whereas something having memory means that the current output not only depends upon the current input, but may depend upon previous inputs. So in our calendar circuit, that's what was happening, right? I mean, when the clock tick came, then we stored the input into that blue box, and then from that point on, my output is actually reflecting the past, whatever is in that box, not what the input to that box is. Okay, so memory basically means that my output depends upon something that we saw in the past on the input, and not necessarily just the current input. Okay? So sequential logic circuits, that particular one which we had seen before is an example out here. So what's happening out here is that this output, it's always going to reflect whatever is stored in the register. And I may change the input values out here, but as long as there is no clock, the output will not see that change. So the output is seeing what was stored there at some point in the past when that clock had come. And from that point on, the output and input are decoupled in this particular example. So it's an example of a memory full behavior. So there is some storage area out here where we are storing the values, and those are the ones which we are kind of outputting out here. So our calendar circuit is an example of it, but in general, our computers are an example of it, right? I mean, whenever in a program you use a variable, for example, that's stored in the memory, and then at any given point in time, your output of your program may be the result of a variable which you had read long ago, perhaps even years ago, and was sitting in the disk or somewhere else in the computer memory. So computers are, by their very definition, have memory. They have DRAMs and hard drives and flash memory, so they have tons of memory. On the other hand, computers do have pieces of combinational logic, lots of them. Like for example, if you add two numbers, then at the time you are doing the addition, that addition function is a combinational function. It takes two inputs, produces an output, we are done with it. Adder does not have a memory in them. It does an instantaneous function and it kind of moves on. So combinational stuff is the building block, and then we sort of combine them together with these registers to create kind of what you see from complete computing systems. So sequential is what eventually one has to design, but combinational is a critical sort of base to do that. Okay, so that kind of wraps up this previous module. So next thing we are going to do is we are going to start on now how to design the combinational logic. So we'll come to sequential logic after the midterm. For now, we are going to focus on combinational logic. And the first thing is really kind of how can we design these things in a systematic fashion. So the way to do this thing is to first kind of understand what the rules of the game are. So we kind of saw that there are these things called gates, and that we can combine them together to make more complicated things. But the question comes up, how do we kind of combine them? And it kind of takes us back to like when we first learned algebra or arithmetic, we are taught about numbers, operations on numbers, like you can do addition, subtraction, and stuff like that. And then from that, we kind of create more complicated things. In the same story out here, we're going to start with bits, and we're going to see how they can be operated upon. So this is chapter 3. So what we are basically doing in this module is to create an algebra, create a Boolean algebra. So where our variables are limited to being binary variables, logic 0 and logic 1, as opposed to a regular algebra that we learn in middle school, which is over real numbers or integers and stuff like that. So Boolean algebra is an algebra where our variables can only take values 0 and 1. And the operators, there are three operators we define: an AND operator, an OR operator, and a NOT operator. And in the parentheses after that, you see kind of the symbols that the textbook is using and that we are using in the lecture. There are alternative symbols that people use. I'm going to comment on them. They might be fine in general, but for this course, you're expected to use these particular symbols. So an AND operation is simply the following. If I have two variables, A and B, then A and B is 1, if and only if A is 1 and B is 1. This is exactly our AND gate that we saw earlier on. So what that means is if A and B are my two input, then A and B is 1 only if both A and B are 1. So the bottom row out here, as you can see, it's showing that. OR operation. A or B is 1 if A is 1 or B is 1. Or another way of saying is A or B is 0 if and only if both of A and B are 0. And you kind of see that out here, that A or B is 1 for the bottom 3 rows out here. So this is simply the definition. Much like we define addition in regular algebra, we define and OR in this algebra. Not operation. Not operation takes a variable and outputs the invert of that. So if A is 1, output is 0. If A is 0, output is going to be 1. So it inverts that. A and B, these are our variables. The name that that is used in digital systems is they're called literals. So think of them as the XYZ variables that we kind of see in regular algebra. These are just represent counterparts out here. So the truth table of a NOT operation looks kind of like this. If A is 0, output is 1, and there's another row where A is 1, output is 0. So these are just definitions. There is nothing sort of that we have derived on this one. Now, a note on the notation, as I was saying, I'm using these notation sort of the V shape for OR and a caret sign for the AND. You would also see that sometimes a vertical bar is used for OR, and sometimes an ampersand is used for AND. And that is also fine. In some places, OR is represented with a plus sign, and AND is represented with a multiplication sign. And I would strongly recommend not to use it, because in regular algebra we use it, but unfortunately some of the properties which are true in regular algebra are not true here at all. Strongly recommended to kind of use this, either the V sign or the vertical bar, and likewise the caret sign or the ampersand. Do not use plus and multiplication signs. If you want to OR a whole bunch of things together, you can use sigma sign. And if you want to AND a whole bunch of things together, you can use the product sign, the pi sign. So these are again just notational things. So now let's see how we can make use of this to formally describe digital functions. Thus far we saw them as truth tables. The problem with truth tables is that it's good for humans, you can draw it, but if you are writing software which is going to help design digital logic and all, then you need some representation which software can manipulate, and combination doing it as equations, as algebraic equations, helps us do it. So let's look at a circuit. What we want to do is we want to take 3 inputs, A, B, and C, and what we want to do is output a 1 if more inputs are 1 than a 0. So it's called a majority function. If majority of the input bits are 1, we are going to output 1. If majority of input bits are 0, we are going to output a 0, and assume that the number of inputs are odd, in this case 3. So if you look at this, if A, B, C, 0, 0, 0, all are 0, output is 0. 0, 0, 1 with second row, 2 of them are 0, 1 of them is 1, so majority is 0, so output is 0. And the same thing goes on until we hit 0, 1, 1. Now 2 of them are 1, and therefore output is 1. And if you go down, again 1, 0, 1, output is 1, and so on and so forth. So this is our truth table. And now to write it down as a logic equation, as an equation in our algebra, what we can do is we can look at which entries of the truth table are 1. So if you look out here, there are 3 entries of the truth table which are 1. One corresponding to A, B, C being 0, 1, 1. Another, 4 of them. And then the bottom 3 rows. And we can play some magic, and which we're going to see in the next module, to come up with a logic equation corresponding to that. And in this case, for now, treat it on trust, logic equation looks like this. It says that output Q is A and B, or A and C, or B and C. And if you think about it, what it's doing is it's covering the three cases. It's basically saying output is high if A and B are 1, or A and C are 1, or B and C are 1. So those cover the thing. Now what happens if A, B, and C, all three of them are 1? Then what will happen is that A and B will, the first clause will be 1, the second clause will be 1, the third clause will be 1. We are ORing them together, we'll still be back to 1. So this equation captures whatever is in this truth table. We can check whether it remains true. Let's take A, B, C being 0, 0, 0. Then A 0, B 0, C 0. So A and B is 0. A and C would be 0. B and C would be 0. And all of them put together would remain 0. So to write it out, let's say this was our case. So let's say we are considering, so if we are considering this case, then A and B is going to be 0 and 0, which is 0. A and C is going to be 0 and 0, which is 0. And then B and C is going to be 0 and 0 equal to 0. So all these three terms, this is 0, this is 0, and this is 0. And so what we end up with is 0 or 0 or 0, which again is 0 because it's an OR gate. So this equation appears to be true. If you try it on every row for the truth table, you'll see that it matches, its output matches the output that we expect. So I can describe a combinational logic function in terms of this algebra that we have defined using the AND operator, OR operator, NOT operator, and these variables. So what this algebra, this Boolean algebra lets us do it to think of our circuits as equations, and then we can apply mathematical techniques to play with those equations, simplify those equations, factorize them. So pretty much everything that you do on the arithmetic side to do computation, I can now do computation with these Boolean things. So again, if you kind of go back to your math classes, when we first learn about algebra and when we are first taught about plus and multiplication and all, we are also given rules about it. So like for example, addition, we are told about rules like a plus 0 is a plus b is the same as b plus a. What is that called? In regular algebra, when we say a plus b is b plus a, what is that property called? Huh? Commutative. Yeah. Then we have the property a times b is the same as b times a. The same property for multiplication. We are told about distributive property. We are that a times b plus c is equal to ab plus ac. So all these properties we are told, and they kind of form the rules of the game in terms of which the algebra is done. It's the same thing with Boolean algebra, but the rules are slightly different and some properties are different. So set of mathematical statements which we claim are true. So first one is identity. So in regular algebra, we are told that a plus 0 is a. So 0 is 0 basically has the property that it does not cause any change in the addition operation. Likewise, a times 1 is a, so 1 is the multiplicative identity. Same thing out here. 0 and x is 0, because if, remember, an AND gate or an AND operation, for its output to be 1, both inputs have to be 1. So if I say 0 and x, then whatever be x, output is going to be 0. 1 or x, output is going to be 1. Idempotence. This is another property which basically says 1 and x is x, and 0 or x is x. So if I AND anything with 1, the output is that whatever I started out with. And if I OR anything with 0, output is the same thing we started out with. Again, these are just definitions. There is nothing. This is how we define the properties of these two operators, the AND operator and the OR operator. Negation. Not of 0 is 1 and not of 1 is 0. This is how we just define negation or not or inversion. Starting with those axioms, we can then derive a whole bunch of useful things which turn out to be useful in designing digital systems. So let's look at some example. One is the commutative property. So it basically says if you are ANDing two things, it doesn't matter what order you AND them in. So if I have an AND gate, it doesn't matter which input I tie the variables to. The order doesn't matter. And same thing with the OR gate. In regular arithmetic, addition, multiplication are order independent, but minus is not, division is not. So not all operators are necessarily commutative, and OR are commutative. Associative. This again follows from our regular algebra. So it's basically saying x and y and z is the same as x and y and z. So if I have to AND three variables, it doesn't matter whether which two I AND first. I can either AND y and z first and then take the output and AND it with x, or I can do with x and y. And the same property holds true for OR gate also. So again, in counterpart in regular arithmetic, multiplication is associative and so is addition. But on the other hand, is subtraction associative? So if I'm trying to do A minus B minus C, and what about division? If I'm doing A divided B divided C, that's kind of the order matter. So I'll let you think about that. We don't have subtraction and division out here. So distributive, it basically says that if I'm doing X and Y or Z, then that's the same as doing X and Y or X and Z. This is equivalent to the corresponding property in regular arithmetic. Same thing holds true if I have X or Y and Z. So do you see, anyone sees a difference out here with regular arithmetic? So let's say we were to think of AND as multiplication and OR as addition. What we are saying is AND distributes over OR and OR distributes over AND. Both are true. In regular arithmetic, is that true? Can I distribute multiplication over addition? So can I say A times B plus C is equal to A times B plus A times C? That's true. What about the other way around? A plus, within parentheses, B times C. Is that the same as A plus B times A plus C? It is not. Right? So regular arithmetic, only one of these has only one distributive thing, regular algebra, whereas here both are true. And this is one of the reasons why it's a bad idea to use plus and multiplication in lieu of OR and AND gate. The earlier slide we had, because it can be very misleading in the Boolean case. In the Boolean case, both the distributive properties are true. Idempotence. X and X is X. X or X is X. Again, kind of from the intuitive definition of AND and OR, that kind of stands to reason. So that's called idempotence. By the way, just to kind of put you at ease, you don't need to remember these names, but what you do need to know is that these properties are true because you're going to need it as you're designing stuff. Okay. absorption property. So what absorption is saying is x and x or y is equal to x. And likewise, x or x and y equal to x. So can anyone help me out? Like, why do you think this is true? How can you prove it? So we want to prove that this statement is true. So, and everything we have discussed thus far, those axioms and the 4 properties above, those are available to us. So, how would you prove that this absorption property on the left-hand side is correct?
It will always be an x or x and y.
Okay, so which property you are applying? Okay, so we have x, this is equal to x and x, or x and y. That doesn't really help us, right? Okay, so let's try a different approach, a brute force approach. What are the possible values of x and y? There are 4 possibilities, right? X and y can be both 0, 0, 1, 1, 0, 1, 1. So one way of going around proving this thing is you just draw the truth table. So list down x and y, and I'm going to list out x and x or y. If it is both 0 and 0, then x or y is 0, 0 and 0, 0. So this is 0. If it is 0 and 1, x or y is 0 or 1, so that's 1. And then x and 1, x is 0, so this is 0. If I do 1, 0, then I'm going to be 1 and 1 or 0, which is 1 and 1, which is 1. And then finally, if it is 1 and 1, then this is the same as 1 and 1 or 1, which is again 1. So as you can see, the right-hand column is the same as x, and therefore the property holds true. You can do the same thing for the right-hand one. So absorption property, you can always kind of derive it this particular way. Try to think how you might do it without drawing the truth table in terms of just the algebra, the rules that we have learned thus far. Another property, combining. Combining property says x and y or x and not y is x. So it's basically saying if I combine x with y as well as with the negation of y, then I get back the x. So, another way of thinking is I have x is, so we are basically saying if x is 0 and y is 1, and we are also covering the other case, x is 0 and y is 0, then I've covered both the cases of y, it kind of cancels out. So it's sort of a, we can factor out away y and we are left with x. And likewise, this property holds true out here, which is x or y and x or not y is equal to x. Again, I'll let you kind of work it out. These properties are just kind of a dry listing of what holds true. But knowing these are useful as you simplify the circuits. Probably the most important property which is used is the following. It's called DeMorgan's theorem or DeMorgan's property. It says not of x and y is the same as not x and not y. And likewise, not of x or y is the same as not x and not y. Another way of saying is, this left property is saying that if I have a NAND gate, right, which is the left-hand side, it is the same thing as first inverting and an OR gate. So I can take a NAND gate and I can take this inversion, move it to the input. So instead of inverting the output, I can invert the inputs and I can replace AND by OR. So this is OR. Sorry for the bad drawing. Okay. And this one is saying the same thing. It's basically saying if I have a NOR gate, I can change it by inverting the input and replacing the OR functionality by the AND functionality. Okay, so looking at this, and then if you go back earlier on, I was saying that NAND gate is universal. If you recall that with NAND gate we can implement everything, and we have shown that using NAND gate we could do a NOT, and from that we could do an AND function. But we have not talked about how you could do a OR function. So now let's say I give you a NAND gate. How can you implement an OR gate out of it? Again, the problem is I'm giving you a 2-input NAND gate, and you can have any number of them, and I want you to create an OR gate out of it. So this thing should kind of give you a clue. The bottom figure. Anyone want to take a shot? Go ahead.
So first one, because we already know if we connect the two inputs together, the NAND gate will become a NOR gate. So
It becomes a NOT gate.
yeah, NOR gate.
Right. So the NOT we know how to make. We know how to make an AND gate, and we of course have an AND.
And we just include the NAND gate in front of the X and the Y. I mean, modify NOR gate in the X and Y. So the equivalencies will cancel the NOR gate in the second one. So eventually.
Do you want to come and drop? Thanks for doing it. But you seem to be on the right track, so yeah. Let's see. Okay. Okay. Okay, excellent. So what he has done is he has taken. So what I want to do is I want to create X or Y, right? And so what he did is to take the two inputs, feed them into a NAND gate which he has tied together. So what we have out here is opposite of X, and what we have out here is opposite of Y, right? So negation, because these are nothing but effectively NOT gates. So now what we have is a NAND gate and X and Y feeding into it. But if you look at our figure up there, what it says is that a NAND gate I can replace by, this NAND gate I can replace by OR gate, right? With has inverters at the input. That's what DeMorgan's theorem tells us. And then these two inversion in series will cancel out, and likewise these two will cancel out, and I end up with X or Y. Okay. So what we have shown is that now using a NAND gate, I can also implement an OR gate. And of course, I can therefore also implement a NOR gate, because all I have to do is to feed it through another NAND gate out there with inputs tied together. So NAND gate can be used to implement all the gates that we had on that slide in the previous module, other than XOR gate. We haven't talked about that yet. Likewise, using the right-hand bottom right theorem version of DeMorgan's, we can use a NOR gate to implement a NAND gate and an AND gate. So we can kind of implement everything. So this DeMorgan's is extremely important. Kind of remember it by heart. You should be very, very comfortable with kind of manipulating it. Of course, the others are also important, but DeMorgan is a very powerful one because it lets you go from AND to OR to AND. Any questions on what sort of we did on the board out there? Like why is it kind of working? Okay, we'll go over it more in discussion sections also, but so DeMorgan's theorem, the proof for it can again be done using our truth table approach. So all we have done out here is we have listed all possible values of x and y, and then the left-hand side of the DeMorgan theorem and the right-hand side of the DeMorgan theorem, and we see that the two are the same. So you can kind of work it out manually, but basically, I mean, these are true statements, just mathematically. So let's apply. So these properties that we have learned, let's see an example of how one could use them to simplify equations. So let's say I give you this Boolean function. It's some complicated looking thing. It says f of a, b, c is a and b, or a and b and c, or not a and b and c, or a and b and not c. Some random looking gunk out there. The first thing we can do is we can apply absorption property. So let's go back. Absorption property said x and x or y is the same as x, and x or x and y is the same as x. So what is happening out here is we are going to apply absorption property. So the way we are going to apply absorption property is let's see. So we are starting with this top one. We are saying a and c or a and b. So the first two terms are the same as what we had out here. The next term is not a or b, or a and b and c. So let's see. Let me get my bearing straight first. So this term is the same as the term out here. This term is this term out here, and this term, a and b and not c, is this term out here. And so the first thing we are doing is we are just basically replicating the second term 3 times. So I can always replace x by x or x or x. So in this case, think of x as this a or b, or a and b and c, and what I've done is I've replicated it 3 times. So I took my original expression and then took this guy and then OR it with the first term. I also, in the second line, I took the same guy, OR it with the second term. In the third line, I took the same guy and OR it with the third term. So going from here to here, all we are doing is we are basically saying x and x is the same as x or x or x. Next step we do is, if you look at the first term, a and c or a and b and c, this is where we apply absorption property. So we have a and c, think of a and c as x. So what we have is x or x and c. So if you think of this guy as x and this guy as x, then absorption property says that x or x and c is the same as x. So what we are left with is a and c. This term disappears from absorption properties. So now we have a slightly simplified equation. Now we apply combining property. So what was the combining property? Let's go back. Combining property said that x and y or x and not y is x. So if I go back out here, if I apply the combining property, what we see out here is if you look at these terms out here, so B and C is common in the second row, and we have not A here and we have A out here. So they cancel away and we are left with B and C. So that's what we see out here. So we apply combining property to row 2. And likewise in row 3, if we apply combining property, then we have A and B, and then we have C here and not C here. So that C cancels away and we are left with A and B. So we are applying combining property to row 2, and we are applying combining property to row 3 out here. Whereas in this one, we were applying absorption property to the first line. So we combine all of that, and we end up with this function which says FABC is A and C, or B and C, or A and B. We started out with this, which looks, at least you would agree, it looks more complicated. It has more operations than this guy. What does this function do? Majority. We saw that a few slides ago. Okay, so this top function is also the majority function. It's just implemented in a more complicated looking way. You simplify all of this and you end up with this guy out here, which is how we kind of started out with. So systematically applying these rules kind of by playing with the algebraic equations can simplify stuff. Much like, again, when we first learn algebra, we are often asked to kind of factorize things, simplify expressions, stuff like that. It's the counterpart out here. And there are software tools which do it for you. You feed them these Boolean expressions, and they can apply all those rules and kind of simplify them to give you an easier circuit to implement, or a circuit which is easier to understand. Does anyone know of any software package which does this kind of stuff for regular algebra? Like some of the TI calculators have symbolic capabilities. You feed them a quadratic equation or a polynomial and it factors it out, right? I mean, so what it does is it applies the rules of algebra. Or like, for example, anyone heard of Mathematica, right? Mathematica is a program which can do calculus over some symbolic names and all. I mean, a good way of, you know, once you're old like me, I've forgotten all my calculus. Whenever I need it, I kind of just go there and try it out, right? So there are these symbolic mathematics programs which know how to do it very well. They do it over regular algebra. There are similarly programs which do it for Boolean stuff. It's just that the programs which do it over Boolean stuff are used for very specific purposes, for designing hardware, and they are immensely costly. So they're used by people who design computer chips and stuff like that. But they exist and they are designed to be very fast because they work with large chips with billions and billions of gates, so they have to kind of process things very rapidly. So under the hood, they basically apply these kind of rules and all to kind of come up with the solutions. Okay, so those are the basic rules. Then it turns out there is another very interesting property that Boolean logic has, and it's called the duality property. And DeMorgan's theorem is a special case of that, the one which we saw where and or were replacing. So the idea behind duality is the following. If I take a Boolean function, some f of some variable, and wherever I have and, I replace it by or. Wherever I had or, I replace it by and. If I had a 0 anywhere, I'll replace it by a 1. If I had a 1 anywhere, I'll replace by a 0. So for example, if f of ab was this function, a and b or b and c, then dual of f, which we are going to indicate with this subscript d, is A or B. So basically we have replaced this and by this or. This or I have replaced by and this and I have replaced by this or. So we map to the dual, and this is called the dual function. Now, that's just a definition of duality. There's a very interesting property which is true, which we'll see shortly, but let's do this following first. Give me the dual function of this. So we are given the function f of x, y, z is x and not y, or not x and z. So anyone wants to take a shot at this? So we want to come up with okay, so first, how would you go around doing it? So we are replacing all the ands by ors, all the ors by ands. So this middle stuff will become or here. This guy will become and. This guy will become or. Okay. And what else? That's it, right? So the rest you can just copy over, okay? So essentially, okay, so now duality property. The duality property, which is very important. What?
You said on the previous slide that you went 0 with the 1 and 1.
If it was a literal 0, there was like a 0 or a 1 appearing in your equation.
The truth table, right?
Not in the equation. So I can always have an equation that says x and 1. Okay. So dual of a function applied to complement of an input variable equals the complement of the function. So what is it saying? It's saying that if I find the dual of a function and then I negate all the inputs to it, so wherever I had x, I replace it by not x, wherever I had y, I replace it with not y, and so on and so forth, then that function, that dual of the function, the dual function over the negated inputs, its truth table, its value is the same as my original function. So what it means is the following. It's basically saying if f of d is a dual function, then f of d done over all the negated inputs is the same as the negation of my original function. Okay, so now DeMorgan's thing is just a special case of it. In DeMorgan stuff, we are basically saying, so firstly, let's take x and y. Okay, let's say my function was x and y. The dual of this function is x or y. Dual of that function applied over x and y inverted is this, not x or not y. And what our duality theorem says that this guy is going to equal to my original function with a negation in the front. That's exactly what DeMorgan's theorem said. So DeMorgan's theorem is for a very special f. It is giving me, it's following this property. The other DeMorgan's theorem is this. So here my function was x or y. Its dual would be x and y. I'm going to replace x and y by the negative. So I get not x and not y. And our duality theorem says that not x and not y would be my original function x or y, but the whole thing inverted. So I have inversion in the front. So DeMorgan's theorem is a special case of a more general property which says that negation of a function is equal to the dual of the function applied to the negated inputs. And I'm not proving these are kind of complicated enough to prove, but so you have to just take it on a trust basis. But it's a very powerful thing because you can really move very rapidly from very distinct functions. And one of them, oftentimes, in some technologies, a dual may be very cheap to implement, whereas the original function was not. Like for example, in many technologies, AND gates are good, AND gates are slow, OR gates are fast. So whatever function we have, we try to replace AND gates or NAND gates by NOR or OR so that they are faster. So DeMorgan's or this duality property kind of ends up helping us out. Now, if you think about it, there's no counterpart to this duality property in a regular algebra. I cannot replace plus by multiplication and multiplication by plus. That is kind of the concept. So again, while there are some parallels to our regular algebra, this is a different algebra with its own properties and its own theorems and things that help us out. Okay. Another definition, midterm. So I'm throwing a lot of definitions at you, but we're going to be using all of these in subsequent modules. So unfortunately, there's no way around them. So midterms. Again, something you have to be very familiar with. A midterm is an expression which ANDs together a bunch of variables or their negated forms. So if I have variables called A, B, C, D, let's say, a midterm example might be A and B and C and D, or A and B and C, not D. So I have to make use of every variable. I have to AND them together, but some of the variables can be negated. Okay, this is just a definition. There is nothing fundamental about it. So for example, let's say I have a function with three variables A, B, and C. Then some possible midterms of them are A and B and C. Another possibility is not A, not B, not A and B and C. Another one is A and not B and not C. I'm just kind of listing some of them out. How many midterms do you think this function has? 8, right? I mean, each variable can occur in its unnegated form or negated form, and I have 3 variables, so 2 times 2 times 2. So I have 8 possible midterms. How many rows did the truth table of this function have? 2 Yeah, or 3 or 8, right? I mean, the same 8, right? So the thing that I'm trying to draw your attention to is these midterms actually correspond to rows of the table. There are 8 midterms, there were 8 rows, and each entry like 0, 0, 0 corresponded to a midterm which was not A, not B, not C. 0, 0, 1 corresponds to the midterm not C, not B, A, and so on and so forth. So there is so midterms is a concept which will let us deal with truth tables nicely in our framework. How many midterms does a function of n inputs have? 2 to the power n. Okay, that's the same as number of rows in its truth table. Another definition, which is the dual of this, it's called max term. So, anyone wants to take a guess of what a max term might be without looking at the slides? Dual, right? So, instead of AND, we are going to use OR. So, max term is now all the variables used and ORed together, but some of the variables might be negative. Okay, so in our case, it's an expression that ORs together. So FABC max terms are, oh gosh, I made a typo out here. Some of the max terms are A or B or C, not A or B or C, and so on and so forth. And again, the number of max terms would also be 8 in this particular case, and again to the power n out here. So now let's write down. So I have some function out here of 4 variables. So if I do the truth table, there will be 16 entries, and I can label them 0 through 15, essentially kind of corresponding to the binary number corresponding to these things. And I can write down the minterms out here and the max term. So for example, this first midterm where D, C, B, A are all 0, we are going to write it as not D and not C and not B and not A. Likewise, the corresponding max term we are going to write as D or C or B or A. So see, for max term, we are going to invert the notion out here. For min term, we use it like this. And we kind of write this. The second min term corresponding to 0, 0, 1 is not D and not C and not B. So D, C, B were 0 and A, because A was 1 out here. Corresponding max term is going to be D or C or B or not A. So max term, again, if you see, we have non-negative appearing wherever we have the 0 and negative appearing, negated appearing wherever there is 1. And we can kind of do this thing for the entire table. So like if we go out here, let's say 15, 1, 1, 1, 1, min term is D and C and B and A. It's basically saying D is 1 and C is 1 and B is 1 and A is 1. And for the max term, we are going to say not D or not C or not B or not A. Okay, it's this because everything is a 1 out here. So we'll see kind of later that how these things kind of help us. Right now, these are just definitions. Now, instead of listing out these min terms and max terms like this, there's a compact notation which is often used. And what we do is we call min term which corresponds to row number 0 to be min term number 0. Min term which corresponds to row number 1 to be min term 1, and so on and so forth. So for example, this shaded entry, which is in row number 2, with the row starting from 0, is called M of 2. And the little m means min term. Okay, again, just a notation. So instead of writing out not B and not C and B and not A, I can simply write M of 2. And the idea is it's understood that it expands into this expression. What about max term? Max term notation is a little bit trickier. So whatever is the row number, we are going to subtract it from the maximum row number, 15. So like this entry, which is at row number 9, we are going to say that it is max term number 15 minus 9 or 6. So, or another way of saying is we are counting from the bottom. Okay, so the bottommost max term is max term 0, max term 1, 2, 3, 4, 5, 6, all the way through 15. Question?
Can you also just look at the min term and find the one with the same corresponding thing, but with like ands instead of ors?
Yeah, so the corresponding max term, the max term corresponding to the min term is all the ands are replaced by the ors, and all the literals are inverted, right? So that's what we are kind of seeing out here. The naming convention is that we start from the bottom. Okay, so this is big M of 0, big M of 1, and then this is max term number 15. Okay, and again, like this is a convention. There is nothing kind of magical about it other than it makes some of the manipulations later on easier to do. Okay, so now that we have defined these min terms and max terms, the next concept where they feed into is this notion of a normal form of a Boolean function. So the idea is I give you a Boolean function, and you can, and we saw for the majority function that we could write it in a couple of different ways. And in fact, generally speaking, you can write a function in many different ways, right? I mean, I can take my expression and massage it using my rules of algebra and come up with an equivalent alternative. But there is going to be one unique representation that we want, so that when we say you write the Boolean function and for the same function I'm going to write an expression, we want to be we want to do it the same way. So there is something we are going to kind of agree upon, and that is called as the normal form of a Boolean function. And what the normal form of a Boolean function does is, it is called sum of products. That is, we take some minterms and add them together, and order them together. Or it's called conjunctive normal form. What does conjunction mean in English? Plain English. Conjunction, disjunction. Anyone heard of these terms? Conjunction means and, disjunction means or. Okay. So conjunctive normal form means I'm taking the and terms, which are the midterms, and then I'm going to OR them together. So let's see how it works out, why it is called this way. So f of a, b, c, if I were to write, let's say this function was f of a, b, c, or f of a and not b or not c, or f of a or a and not b, not c. What is, if I, in my compact notation, what minterm is this? So if you think of the truth table, which entry is it on? The 8th row, or which would be 7 in our convention, 0 through 7, right? So this is m of 7. What about this guy? So it depends upon how you write A, B, C. If you write it as A first, then B, then C, then it's m of 4. Okay. Usually in our tables, we are writing it as C, B, A, in which case it's 0, 0, 1. So it's actually m of 1, because we write it as C as the most significant one and A as the. What about this guy? M of 5. So we can basically say that this function is m of 7 or m of 1 or m of 5. So I have written my function as a OR of 3 minterms. And this is called sum of products. If you think of OR as the sum and as the product, that's where kind of the name comes from. So this is a conjunctive normal form. Disjunctive normal form is its counterpart, where what we do is we take several max terms and we AND them together. So an example out here of FABC is that now I have taken several max terms, each one of these things in parentheses out here. This is a max term, this is a max term, this is a max term. Okay, so help me out now. What max term number is this? M of 0. This is M of, well, so 1, 0, 1, or another, so 0, 1, 0 says M of 2. What about this guy? M of 6, right? And again, those of you who are not following, it's M of 6, because what I can do is wherever I have a positive variable, I'm going to put a 0. Wherever a negative variable, I'm going to put a 1. And then I'm going to read from the other direction, because I think of C as the MSB. So most significant bit. So it's 1, 1, 0, which is 6, M of 6. So notation wise, what we end up with in this case is M of max term 0 and max term 6 and max term 2. And this is the disjunctive normal form. Now, the advantage of these two forms is, if I give you a truth table, you can literally just write it down immediately, right? I mean, I basically look at the row number, and if I say write the sum of products, you can immediately just look at the row numbers and kind of write down the midterms and OR them together, or you can write down the max terms and AND them together. So coming up with a normal form representation of a function basically means you should have the truth table in front of you, and you can just write it down immediately. It's not very efficient because we'll have a lot of minterms. Like let's imagine I give you a function where half the rows have output 1 and half the rows have output 0. Then I'm going to have, if I have n variables, then 2 to the power n minus 1 minterms and 2 to the power n minus 1 max terms in my two forms respectively. So it can be very expensive depending upon the nature of the function. But it's a standardized way. So conjunctive normal form is used most commonly. And the reason actually has to do with just plain technology, as in most, in the popular, in the commonly used electronic technologies, it turns out sum of products is cheaper to implement, it's faster, smaller in silicon area than the distinctive normal form. So usually conjunctive normal form is the one which we simply call as normal form. Sum of products or sum of minterms is commonly used thing. So why normal form? So thus far it was just a definition. I can list it this way, but why? So firstly, it's unique. If we have a function, if you were to write its normal form, if I were to write the normal form, we are guaranteed it will look the same. So what we can do is we can compare whether two functions are equivalent. So if I say, hey, I have a box which implements a digital function. You claim you have one also. We want to find out, do they do the same thing? And one way of doing it is we say, tell me the normal form representation of your box, and I'll come up with the normal form representation of my box, and I can then just compare. If they use exactly the same set of minterms, then they are equal. Otherwise, the two functions are different. So normal form is unique. Normal form makes it easy to compare whether two functions are equal or not. And this is kind of easier than kind of trying to compare the table. So that's kind of the logic out here. So let's look at our good old thermostat example again. So this is a truth table. What is the normal form of this? Again, by normal form we mean sum of products or conjunctive normal form, or taking the midterms and origin together. So can anyone help me out? What would the normal form of this guy look like? So step one, look at where all the function is 1. Which rows is it 1 at? So if I mark them out, let me. Then we have this guy. We have this guy, we have this guy, this guy, this guy, and this guy. So I have 6 minterms, or 6 rows where it is 1. So all I need to do is to write down the corresponding minterms and OR them together. So let's start with, what is this minterm? Anyone? Someone? 8, right? It's the row number 9, so it's m of 8. And by that logic, the next one is m of 9. 10, 11, 12, so this is plus m of 12, plus m of 13, plus m of 14, plus m of 15. And that's my normal form. And by the way, what I'm falling into the trap that I told you to avoid, so it's actually all OR. Okay, so it's m of 8 or m of 9 or m of 12 or m of 13 or m of 14 or m of 15. And intuitively what it's saying is that the function is true if the inputs belong to one of those rows. So if one of those minterm is true, then the function is true. That's all that this thing is saying. Okay, so that's the normal form for this function. And next few slides, we kind of work it out. It's basically kind of listed out here. Okay. Find the dual function of the following function and write it in its normal form. So we are given a function, f of xy is x and not y, or not x and y. So what is its dual? Yeah, say it loudly. X or not y, and not x or y. Okay, excellent. So that's my dual of the function. And what you have to do now is to write out its normal form, its conjunctive normal form. So how would you go on doing it? One way is to do the truth table. Okay, so let's do the truth table. So we have x of y, and then we have f of d x of y. 0, 0, 0, 1, 1, 0, 1, 1. Okay, or actually, since we have been, let's call it y out here and x out here. Okay. So what's the first row? Both x and y are 0. So we have 0 or 1, which means it's 1. And we have 1 or 0, which is 1. So it's 1 and 1, which is output is 1. What about next guy? Y is 0. So the first term becomes 1. X is 1 here, so the second term here is 0. So we have 1 and 0. Output is going to be 0. Likewise, this term is going to be 0. And the final term is we have 1 or 0. So the first term is 1. The second term is 1. We have this guy 1. So now what's the normal form of this? M of 0 or M of 3. Okay, so that's my conjunctive normal form. I'm looking at row number 0 and row number 3. A side question. This truth table, what function does it remind you of? Huh? It's a not XOR. Okay, good. Or is there a simpler English expression of this guy? It's the equal function, right? X equal to y. Then the output is 1, right? So it's the equal function. But not XNOR or not XOR is also correct. Okay. So that was this little example. So now, given the equations, we can very easily map them to gates. And that's a very mechanical process, very easily done. The only thing that we have to basically do is we have to take operator groupings property. So it's much like regular arithmetic. Parentheses are important, and we have to kind of take them into account. And what we'll assume is we are given gates, our good old AND gate, OR gate, NOT gate, and they could come with any number of inputs. In Logisim, you have the same story. When you select an AND gate in Logisim, you can change how many inputs it has. It can go anywhere from, I think, 2 inputs to 5 or 8 inputs or something. You can have large number of inputs to a gate. So the way this mapping works is it's kind of pretty straightforward. Let's look at this guy. So what we have is a function ABC, which is A and B or B and C or A and C, which was what? What function is this again? Majority function. Seen it many times. Okay. So it's a majority function. So we're going to draw it out and mapping to gates. So we start out with this thing and we say, you know, at the top level, I am ORing three things, right? I'm ORing whatever is in this first grouping, whatever is out here, and whatever is out here. So I have at the highest level, I have an OR gate. And it has three inputs to it. And then the first input is A and B, so that's an AND gate. Second input is also an AND gate, but this time it's B and C. So I'm going to feed B here, and I'm going to have C. And the third input is A and C, so it's also an AND gate. It takes C out here, and it takes A out here. Okay, so that's what my gate is, and the output is okay. So the mapping process is just walking through the expression. First, look at the highest level, put it down as a gate, then go inside each of the parentheses and kind of do that process recursively. So this is what it looks like, what I had drawn by hand. And okay, let's try another example. X and not Y, or not X and Y. So anyone wants to take a shot at it? Like, what would be the highest level gate? First thing that I could draw. OR gate with two inputs. Then what? So I have two terms. The first term is what? It's an AND gate. So I'm going to draw an AND gate. Its inputs are X, and the other input is negated Y. And the second input is again an AND gate, but this time around X is inverted. And Y is fed as is, and that's f of x comma y. So going from equations to gates is easy. So now kind of the way kind of the whole design process works out is we are first going to write a truth table or some sort of expression for our logic function. We are going to apply the rules of Boolean algebra to make it simplified, and then we are going to just map it to our gates. And we are going to assume that we are given a supply of these AND gates, OR gates, and whatnot. And that's kind of a simple story. More complicated story is I may not have all the type of gates. I may have maybe given only certain type of gates. So when I'm mapping, I may have to do a little bit of extra work to kind of do it. And then additional complications may come up that you may be told you can only use so many gates, or you must consume less than some amount of area, or your chip should cost less than some dollars, or things like that. So there might be constraints on power, speed, area, dollar cost, time to design. All those kind of things might be there. But at a very high level, the design story is optimize it mathematically and then map it to gates. And the good news is that until mid-80s or so, all this stuff used to be done by hand for the most part. And then sometime in the 80s, software to basically sort of computer scientists worked out algorithms to manipulate these things. And over the course of the 80s and early 90s, we basically ended up with excellent software tools which can do all of this automatically. So you don't have to manually kind of do it. In Logisim, if you go to one of the menus, it's called Analyze Circuit, I think. And in there, you can do these kind of things. You give it a truth table, and it will give you an optimized equation. You give it an equation, it will give you the truth table. It can give you the gates corresponding to your truth table. all of it does it. It doesn't do a very good job at it. It's a simple program. The commercial strength programs do it much better than what Logisim does. But at least in principle, these things are all taken care of at this stage. More primitive gates. We have seen them previously, but just to reiterate, so besides and or, you may be given NAND and NOR. And actually, it turns out that in common silicon technologies, NAND and NOR are the real primitive gates and inverters. Not. So NAND and NOR are available to you, and if you need an AND gate, you have to make it by taking a NAND gate and an inverter. And likewise, if you need an OR gate, you have to take a NOR gate and an inverter. The way silicon technology, the physics of it works out is the basic gates available to us are NAND and are these two, NAND and NOR. And also within that, usually NOR is cheaper and faster than the NAND. So you would often see designs are just done entirely using NOR gate, and inverter is just a special case there. Sometimes you will see NAND gate to be written like this, and NOR gate to be written like this. And why are the two equivalent? Anyone? DeMorgan's, right? This is basically the two being equivalent is just a visual representation of DeMorgan's, and the same thing kind of out here. Okay, so so more likely than not, in a silicon technology, at least, you would have NAND and NOR being the basic things available to you, and rest of the stuff then you kind of implement it. So okay, so what we now have is kind of the basic mechanics of how to mathematically represent and manipulate Boolean logic. And we also know how to take those equations and map it into gates, and the gates can then be implemented in silicon technology. So, kind of the complete pathway out there. What we don't have is how to design these things efficiently. So we can create a truth table and we can write them in those normal forms, but I may have a lot of minterms, and so the design may have lots and lots of gates, and that results in expensive circuits. So what this module we are going to do is learn about how to design these things efficiently, as in my final result is something which is perhaps fast, perhaps small in area, has fewer gates, maybe consumes less power, all those kind of nice physical attributes that would make it good engineering. So this is chapter 6, all the sections you have to cover. And it's kind of a recap again. So we have gone through thus far in the course how to represent digital signals, both in terms of voltages, how to represent information in terms of bits, how to do this Boolean algebra, and we kind of saw the concepts of combinational and sequential circuits. So what is going to happen out here is we are going to see how we can design complicated, somewhat complicated combinational logic by hand. Now, as I said a short while ago, now there are computer programs which do it for you. So one question which comes up is, why do we teach you to do that? The part of the problem is that those programs may not always be available, but the other thing is, this is so fundamental that for you to do a lot of other stuff, maybe someday you might be the one writing some of those programs, and also you have to know kind of the basic process, which is kind of what we do. But in commercial world, if you were to do, you will not be doing it by hand, but rather you will use programming languages. They are called as hardware programming languages. Verilog, in the textbook, they use that quite a bit. And there is another one called VHDL, VLSI Hardware Description Language. I think that's what it stands for. And then the idea is that to design a hardware, what you do is you kind of write a description in these languages. You feed it into a simulator where you give it test cases and see whether it simulates correctly, and once you're happy with it, you hand it over to a tool which takes your hardware description language program, converts it into a file which you then send to the manufacturers, which makes a chip for you. So it kind of looks not very different from the way you write software. You write it in Java or C or some language, you feed it into a compiler, it creates the program binary for you, you can run it. In this case, instead of running it, you send it to a company, usually some of the big companies doing this are like Taiwan Semiconductor, TSMC, for example. Send them your design, they charge a few $1 million, and yes. So the process is conceptually straightforward, okay, but everything is big dollars in this one. Just to give you a sense, the factories which make these chips now, they are drawing the transistors at now 22 nanometers or 14 nanometers, so it's really, really fine thing. And the cost of those factories, each one of them is, latest numbers are somewhere around 10 to 15 billion dollars each. Okay, so these are not tiny little cheap factories. They're super expensive. They're like, I mean, they consume power equivalent to small cities, and kind of really, really complex, expensive things. And certain companies, Intel does it very well, but Intel does it only for itself. They make the chips, does it for their own thing, but they basically Samsung is another very big manufacturer. Again, they make a lot of their own chips. TSMC, the Taiwan Semiconductor Manufacturing, and another called Global Foundry. These are in the business of making chips for others. So, like if you're a little company, you've come up with some bright idea of startup products or whatever, and you want to get chips made, you're likely going to one of these other companies and get things done. Okay, so this module, our goal is to kind of look at how to design these things. Okay, so let's start with an example. So usually your starting point is going to be, you're given some sort of a high-level description of what your combinational logic system should do. So for example, let's say we want to design a function which we will call as prime or 1. What it says is that the output should be high if the input is either the number 1, decimal number 1, or it is a prime number. Okay. So f of DCBA, we are going to think of D, C, B, and A to represent the 4 bits of a 4-bit number, D being the most significant bit, A being the least significant bit. And so it's basically saying that f of DCBA should be true, that is, output should be logic 1. If input DCBA viewed as a 4-bit number is 1, that means D is 0, C is 0, B is 0, A is 1, or it is prime. So prime numbers up to 4 bits are going to be 2, 3, 5, 7, 11, and 30, right? So those are the cases, and then we have 1. So basically what we are saying is, if DCBA represent 1 or 2 or 3 or 5 or 7 or 11 or 30, output should be 1, otherwise output should be 0. Okay, that's the specification given to you, and now we have to design something which implements it. Okay, so just for the sake of those of you who may not be up to date on Boolean arithmetic, so when I said those 4 bits represent a number, what do I really mean by that? So when we do decimal arithmetic, each position in the number is a decimal digit. It can go from 0 to 9, and the value of a number is its positional value multiplied by the digit out there. So basically, the rightmost digit of a number has a value 1, 10 to the power 0. Second digit has the value 10. The third one has the value 100 and 1000 and so on and so forth. Something that we are always taught early on. In the binary one, instead of 10, we have 2, and instead of digit, we have bits. So basically, if I have B3, B2, B1, B0, then the value of the number is B0 times 2 to the power 0 plus B1 times 2 to the power 1 plus B2 times 2 to the power 2 and B3 times 2 to the power 3. So it's basically the positional values are now 0, are 1, 2, 4, 8, 16, so on and so forth. So DCBA represents this number, 8 times D plus 4 times C plus 2 times B plus 1 times A. So when in our original specification, when we were saying DCBA viewed as a 4-bit number, what we meant really was this value. If this value is 1 or 3, 1 or 2 or 3 or 5 or 7 or 11 or 13, then we want the output to be 1, otherwise we want the output to be 0. Okay, so what does 1010 represent? Anyone? What number is that? 12, right? 8 plus, 8 plus 2, 10. Sorry. So it represents 10. Okay, so now going back to our problem, so we are going to make the truth table. So we have listed all possible values of DCBA. Next thing we do is we write down the numbers. So number 0, output should be 0 because it's neither 1 nor a prime. Next one is number 1. Output should be 1 because that's what the problem states. Next row is number 2. Output should be 1 because it's a prime number. Then so on and so forth. So you would see that we have 1, 2, 3, 5, 7, 11, and 13. That's where the output is 1. Otherwise, output is 0. Okay. So what is the normal form of this function? Okay. Exactly. Whichever rows are ones, right? So m of 1 plus m of 1 or m of 2 or m of 3 or m of 5 or m of 7 or m of 11 or m of 13. So if I just have to come up with an implementation, it's easy. I can just create that normal form. We saw how to map it to gates. We are done. Problem is that we are not done because it's in general very, very inefficient. Uses lots of gates and all. So that's where we have to then do some additional optimizations to kind of make it happen. We can list all the rows where it is 1, and these are the ones, and we can then make the minterms corresponding to that. And then we can write it as minterms. This is a notation that you will often see used in the book. We do a sigma m 1, 2, 3, 5, 7, 11, 13, which is another way of saying is m of 1 plus m of 2 plus m of 3, and so on and so forth. So an implementation is pretty easy. The crucial thing is, could we do something better than that? But given this implementation, I can always implement it using gates. Next time around, what we'll see is how can we do a more optimum